gave it away. So what's 2a say? Is that 1?
7, 10.
All right. So a1 is 1. And what kind of sequence is this? Is it going to be D or an R? Yeah, it's arithmetic. It's always adding, so it's going to be D for the difference between 2. So what's D in this case? 3. And I know that AN is A1 plus N minus 1 times D. I figured that out earlier. So now you just got to throw what you know in for this sequence. Every arithmetic sequence can be written like this for the terms. This one, AN is 1 plus N minus 1 times 3. And then if you want to simplify that, is that right? You can see how to simplify this? 3n minus 3 plus 1, so 3n minus 2. Now, I'm about to say something that's really weird, but I think a couple of you might get what I'm saying. If there was a term before, what would it be? If there was a term before this one and it followed the pattern, negative 2. And then from there, I just add 3 times n to it. That's kind of like, I don't know if you really, it doesn't matter if you don't get what I'm just now saying. It's an interesting way to do this problem, so you can skip some of this. If it would have been here, it would have started at A0. I wouldn't need the n minus 1 shit. I just say negative 2 plus 3n, because that's what I keep doing. Just keep adding 3n. It's because we call that first one A1, that's what makes the formula a little worse than it really had to be. If you don't understand what I just said, just do like we just did. That's fine. Nothing wrong with that. What's the next one? Sorry.
3/4, 4/5, 5/6, 6/7.
So here's one. It's not going to have a standard form. It's not arithmetic. It's not geometric. But when n is 1, I get 3/4. When n is 2, they both increase by 1, 4/5, right? So if n is 1, what would I do? So how do you get this answer? If n is 1, what do I do to 1 to make it 3? I add, what do I do to 1 to make it 3? I add 2. And what do I do to 1 to make it 4? I add 3. Now if n is 2, what do I do to 2 to make it 4? Same thing I did before. What do I do to 2 to make it 5? Add 3. So what's the pattern seem to be? N plus 2 over n plus 3. In fact, if you look at number 1, part B, I think it was, the bottoms are the same as what we had because the bottom of that one was n plus 3. I was kind of trying to give you a little hint. This is always more difficult. Trust me. Oh my God. Oh my God. If you do take calculus 2, you'll think back to, oh my God, I didn't even know how horrible this could be. Trust me, trying to find the pattern as a human sometimes is really not easy. These aren't nearly as bad as it could be. What's 2c? 1/2, 3/4.
7/8.
7/8. 15 16. Oh yeah, I like this one. What's true about the top always related to the bottom in this sequence? Exactly how much smaller? 1 off, right? Do you guys see what I'm saying? Whatever the bottom is, the top is 1 less. So if I focus on what the bottom is, I can just put minus 1 on it, and that's the top. Do you guys see that? Whatever the bottom is, the top is 1 less than that. So let's focus on the bottom then. When n is 1, I get 2. When n is 2, I get 4. When n is 3, I get 8. When n is 4, I get 16. The shit works like that. These are all multiples of 2. 2 to the first power is 2 squared is 2 cubed is 2 to the fourth is 16. So what is the bottom going to be? The other way around, yeah. 2 to the n. Because when n is 3, it's 2 cubed 8. So 2 to the n. So what's the top got to be? Top is easy now. Yeah, 2 to the n minus 1. So whatever the bottom is, take 1 away. These are all 1 off from a multiple of 2. 1 off from a multiple of 2. Freaky as shit, right? Now, just to make sure you understand, the whole problem number 2 is not something that's in this book. I just wanted to do it to show you, just to torture you for a minute. You know this about me. Okay. All right, so let's do, I think I paused for my echo. That was pretty good. Let's do 2 more things here. Let's see. Well, it's way early, Jeff, but I really doubt you guys would hurt me that much. Let's see how long this takes. It might take a little while. All right, so I told you when we were doing the arithmetic and the geometric, we got a formula for the nth term for each one of them. Section 14.3 is all about series. Now, if I had this sequence, 1, 4, 7, 10, the series would be 1 plus 4 plus 7 plus 10. And we have a way to say how far I want you to go. Now, obviously, if I said just keep going forever, well, this is going to add to infinity in a way, right? There's not going to be any cap on it. But what if I said only go so far? So what's that going to look like? Well, somebody help me out. Did we just do this one? What was the formula for this one?
A to the n, 1 equals a of 1 plus d.
Yeah. So, okay. And then we got 1 plus 3 times n minus 1. So it came out to be 3 and minus 2. Is that cool? Okay. So that's the formula to find a specific term in a sequence. So now, for series, this is really all about summing. So if I said S1 means the sum all the way to the first element. So if I add all the elements up to the first one, this is kind of weird, I know, but it would just be 1. It's basically the first element. So add 1. Okay, it's 1. S2 would be the sum of the first 2 elements. What do you get? 5. S3, amazingly enough, would be 12, right? 1 plus 4 plus 7. Do you guys, let me stop there for a second. So A1 is let's try this. A3 is the third term. S3 is the sum up to the third term. Sequence is a bunch of numbers with commas. Series is a bunch of numbers with pluses adding together. I like it. So one of the most important symbols. How many of you guys going into statistics? Anybody? All right. So here's a symbol you're going to see a lot in statistics. So this is the immediate way we reference the sum up to a certain thing. There's another way to kind of identify that, and that's using sigma notation. And most of math is really just getting used to the symbols they chose to use and interpreting what they are, like log, for example. Sigma notation is Greek letter sigma. So like sigma, like a fraternity, sorority. So sigma is this letter, the funky E. All right, the funky E. And it stands, it's amazing enough, they said, all right, I want to represent summation, but I don't want to use I want to use Greek letters and make it look all amazing. And so we picked the letter S in Greek. Ooh, it's amazing, we did a great job. So the letter S in Greek for us stands for sum, right? The lowercase 1 in standard is standard. In statistics means something else. We're not going to. So the sum, here's how this works. So let's say I want to sum up to the third one of this. So I'd say n equals 1 up to 3 of this. So what this means is sum these from n equals 1 to 3. So you would get exactly what we got here. So So now I can say, okay, this would be the first, when I plug a 1 into here, what do I get? I get 3 times 1 minus 2 is 1. When I plug a 2 in, 6 minus 2 is 4. When I plug a 3 in, 9 minus 2 is 7. Of course, I get these numbers because that's the definition of this sequence. I like it. The reason that we have that notation in addition to these is because this means sum up to the third from the first. But now I can do something like this. Say I wanted to know the fourth to the sixth. That wouldn't be any of this shit, right? So we have, and also that sigma notation has a lot of other uses. It's insane. Once you get a little further in mathematics, it's basically everywhere. So here, this would be, what would this mean? This would be, yeah, plug a 4 in, plug a 5 in, plug a 6 in, and then add those together. Okay, amazing. Do you guys get this notation? It looks really complicated. If you looked at it in the book earlier, you're like, oh my God, are we going to do this? But now you see how silly it really is. It's just a way to say sum up the fourth through the sixth, one of these. That's all it means. Okay, I like it. So let's before we get to anything specific with arithmetic and geometric, let's just try some of these. What about this here? We use a different letter even. I equals 2 to 4 I squared. So what are you going to let I be? I is going to be 2, and then 3, and then 4. I like it. So when I is 2, I get 4. Plus, when I is 3, I get 9. Plus, 16. So I'm just going to get those squares, right? 29. Cool. I like it. See, so don't make a big deal out of it, right? Nothing major. What about this here? Yeah, it's gross. Have fun. I am here to put fractions in your life. Comes out nice. It's really nice. When j is 0, what do you get? All right, sweet. So you get 0 plus when j is 1, 1/3. J is 2. Yeah, you get 2/4, so 1/2. J is 3. Yeah, you get 3 fifths. Yeah. And when j is 4, 4 6, which is 2/3. So do you see these? That's nice, right? That's a whole 1. And now you just got to add these together. So that'll be 5/10 and 6/10. 5/10 and 6/10. 5/10 and 6/10. 11/10. And so 10/10 plus 11/10, 21/10. Freakiness. All right, so expect some fractions definitely in these things. Okay, how are you feeling so far? Is that, I mean, to be honest, I mean, the get used to the symbol, and then it's just adding stuff. So it's not that crazy. It's just you got to get used to what the symbol is trying to ask you to do. Okay. All right. Here's the last things we'll do, and then we'll get out of here decently early. So just to remind you guys, arithmetic. We got this thing. But now I want to know what Sn. So I need to see if there's a formula for it. Because remember when I was putting S1, S2, we had to do each one. We had to work each one out. But now, sort of like AN has a formula for it, so I can find A80 real easy. Is there a way to find SN? So then I can find the sum of the first 3,000 terms without having to write each one. Shit. So definitely for arithmetic and geometric, there should be. They have a basic definition to them. There should be a way to use that. So here's where the urban legend comes in from yesterday. I teased it. Gauss, supposedly in like the equivalent of third grade or something, fourth grade. The class was going crazy, and the teacher said, okay, you sit down and you add up the first 100 natural numbers, or I send you to the principal's office where they will kick you in the shins. And so they all started working. Everybody's just working. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. That's going to take a while. So he just sat down and started reading his paper. Right? He's like, this will give me some time. Right? Everybody with me? He probably didn't sound it. Gauss, being the little smart ass he is, got done in 10 seconds. Brought it up to the teacher, said, here's the answer. Can I go home? Right? And so the teacher's like, wait. And he said, 1 plus 2 is 3, plus 3 is 6. And he's just checking his answer. And sure enough, Gauss was right. Right? So we're not sure this is true or not. So here's the thing. So let's do that same problem that Gauss was doing. 1 plus 2 plus 3 plus 4 plus 97 plus 98 plus 99 plus 100. So that's the problem they had to do. This is an example of an arithmetic sequence that's been turned into a series, right? Why is it arithmetic? Because every time I add 1 to get to the next element. So whatever we're about to do will work for every arithmetic sequence. So you do remember there's commutativity. I can add whatever order I want to. So what Gauss realized is 1 plus 100 is what? 101. 2 plus 99, 101. 3 plus 98, 101. So he's going to have repeated 101s. How many 101s will there be? Well, it takes a pair of numbers to make it. There are 100 numbers, so how many of them will there be? 50. So it's n divided by 2, however many in their string, divided by 2 for the pair. And how did I get the 101? What's the first way I got the 101? I added A1 to AN, the last one, right? There it is. That's the formula for SN for an arithmetic sequence. So let's do a concrete example, 2 different ways, so you guys buy into this a little more. So it's this many pairs of this. So what is it going to be for this? Let's finish this out. 100 divided by 2 times 1 plus 100. 50 times 101. 50-50. That's so freaky. If you add the first 100 natural numbers, you get 50-50. Kind of nifty, to be honest. Right? Yes, no? Not really, Jeff? You're weird? Okay. So let's do one. Let's do a smaller example so we can do it 2 ways. A little bit easier than all that shit. What if I had 5, 9, 13, 17, 21? I'm always worried that I'm going to add wrong as I do this. So is this an arithmetic sequence? Yes. Let's just find S5 directly. What's S5 based on what I see? Yeah, 14, 27, 44, 65. Is everybody cool with that? Just adding up the 5 numbers. Whoop-de-doo, right? So obviously I don't need this to do this because there's just so few of them. If there are 100 of them, oh shit, yeah, I'm going to use this. But that formula is supposed to work, period. So let's try this out. What's n in this case? 5. And what's A1? 5. And what's AN? A5. What's the last one? 21. So if I do n divided by 2 times A1 plus AN, I get 5 divided by 2 times 5 plus 21. 5 halves times 26. Well, what's half of 26? 13. 13 times 5 is 65. Cool. Same number we got, of course, because that formula works no matter what. If it's arithmetic, based on addition, that formula finds any sum you want to, however far you want it to go. Please let that be a little bit nifty. Just like maybe like that much. Okay. All right. Now, so why was this? I'm going to tell you right now, the geometric one is nowhere near as easy. Why would you expect that? Well, this sequence that we're talking about is based on addition. And I'm asking you to add numbers based on addition. Okay, those go together. That's a stupid easy formula. Geometric one is going to be gross. There's just no other way around it. I'm trying to decide whether or not I want to show you. I think I do. Do they even show you? Oh, they sort of do. Oh, they do. There it is. Sweet. All right. But they don't show you where it comes from. So I'm going to show you where it comes from. Haha. And then we're going to leave. Okay? Let me see. Now just, you can even put your pencils out if you want to. Just watch and go, I'm not getting any of this shit, but I'm just going to keep looking. Just try to follow. I'm going to show you where the formula comes from. You just have to be able to use the formula. So if I have a geometric sequence with A1 and R, is that so far so cool? Tell me. So let me do this to help us out. The first sequence element. Look, I haven't told you shit, and this is the kind of problem students hate. I didn't give you any numbers. Shit. But what's the first element? A1. Okay, good. What's the second element? No. Be more specific. You can do it, guys. How do I get to the next element? So if I had a geometric sequence, starts at 4, and I keep multiplying by 5, what would the next number be? 20. A1 times R. So what's the next element? A1 times R. And what's the next one? I multiply by another R, so I get A1 times R squared. I keep multiplying by R. How many R's did this guy have? None, because they didn't want to go anywhere. 1 step. 2 steps. Plus A1 R cubed. Plus ... Let me say this is going to be Sn. So I want to go all the way out to the nth term. Yeah, we gotta be careful. It'll be A1 times R to the n minus 1. Remember, because the stupid n minus 1 thing. Okay, I can see. See, this is the dilemma. I want to show you where it comes from, but then I turn a lot of you guys off. Whoever I haven't turned off already. You know, like, but just don't freak out. That's the basic idea. That's how you get each element. If I knew what A1 and R was, that's how I would get each element. Right? And here comes the freakiness. If I multiply this by R, multiply everything by R. Not the most obvious thing to do. I'm going to show you why it makes sense. What I'm going to do is I'm going to multiply by R and then I'm going to subtract them. So what's it going to do for me? It's going to kill a lot of shit. I want to get a compact formula for the sum. So there's way too much shit up here. How far could this go out? Well, if n is 18 million, there's going to be 18 million. So here's the idea. I want you to see. So if I multiply R, what's A1 times R? A1R. I'm gonna offset it. So that goes here, right? Did you guys see that? What's A1 times R times another R? A1 R squared. A1 R squared. A1 R cubed. ... What's A1 times R to the n minus 1 times R? A1 times R to the n. I got one more R. Okay, that is nice and freaky. So now what happens when I subtract these things? I'll get Sn minus Rsn, Sn minus this. I get A1 is still here, isn't it? There's nothing here. A1 minus, okay, so I get A1, that cancels, that cancels, that cancels. This is going to cancel here. And then I end up with 0 minus this, minus A1R to the n. Let me stop for a second. Oh, I love it. You guys, I don't care. I'm going to keep going. Somebody just wait for the, get to the end. Sn, I can take an Sn out. That's what I really want to know, isn't it? I want to know a nice compact formula for Sn. Well, now I can just divide by this. See, I can take an A1 out. So I get Sn is A1 times 1 minus R to the n over 1 minus R. That is a single thing that I have to calculate. So if I wanted S80, I could just throw an 80 in here. So it's similar to the AN stuff, right? And the SN that we got for the geometric. Is it as nice? Oh, hell no. We expected that. Maybe. So let's do an example. Let's do a concrete example. Yes, sir.
R can never equal 1, right?
Yeah, good point. R can never be 1. And why, if R is 1,
There's
what?
no difference.
Yeah, there's no difference. So then it's sort of like both geometric and arithmetic and neither at the same time. So that's why this would definitely freak out. Is that cool? Okay, I like it. Maybe. Okay. So let's try a concrete example. Let's do 3. What do you want to do, Jeff? 3, 12, 48, and then, I can't think. 192, right? Multiply by 4. Yeah, that sounds good. Is that geometric? Yeah, because I keep multiplying by 4. I like it. When you add those up, what do you get? 255. No. 255. Okay. So when you add those up, 3 plus 12 plus 48 plus 182 is, we know that. We know it. So we wouldn't use this formula if that was the problem. Dear God, I could just add them up. I can see them all. I would only use this formula if they asked me, add up the first 720. Oh my God, I don't want to write them all down. But let's check it. So this would be S what? 4. So S4 is going to be A1, 3, times 1 minus R. What was R again? I keep multiplying by 4. 1 minus 4 to the 4th over 1 minus 4. That looks nothing like 255 yet, right? So let's see. I get 3 over negative 3, right? And 1 minus 4 to the 4th is 256. We can double check it. 3 divided by negative 3 is negative 1. 1 minus 256 is negative 255. Divided by negative 1 is 255. I did the same thing. Of course I did. Because that's what that formula does. We designed it to do that for us. That is really nifty. I mean, this is probably like the thing we should do first in here is to show you. This is what math is like stupid good at. Pattern? Oh, shit, I'm all over that. That's what math is all about. So that is the formula for any geometric series to find the sum up to however far you want. I like that. Real quick, let me. This is the last thing I'll say. Do you think it's possible to add an infinite number of numbers together and have it come out to be just a regular number? For example, like if I added 1 plus 4 plus 7 plus 10, and I keep doing that forever, is that going to come out to be a number? It's going to come out to be a type of infinity, right? So is there a way to add up an infinite number of numbers and have the answer be just a nice number like 6? There is. So what about this sequence? 1, 0.1, 0.01, 0.001. This is a geometric sequence because I keep multiplying by 1/10. And when you add them all up, do you guys see what happens? See how every element gets out of the way of the one before it? I don't know if that makes sense to you, but you would end up with 1.111111 forever. That's a finite number. It's nowhere near infinity. So when I first say that, people are like, you can't add an infinite number of things and get something that's not infinite. Yeah, you can. You just got to make sure that they get small fast. They got to get small fast so they don't overlap and throw the whole thing off to infinity. All right, that's a little beyond what we have to worry about, but I just felt like throwing that at you. Okay, so to be completely honest, besides a couple of little technical details, we're done with all the curriculum we were supposed to cover. You're all like, that's nice. I'm back in chapter 12, so shut up. So you got to catch up this weekend. That's what I would highly suggest, is you catch up with a little homework. Monday I'll have the practice test we'll do together in class. I'll have the answer key. Next day is the test. I'll have the practice final on that day. Wednesday is the review for the final. Thursday the final. Friday you go somewhere and just lay down and just drink or whatever you want to do. Okay.
So we're going to do a review before final, right?
Review for the final, yeah. That's